This is a video from section 12.5. The directions say to find the equation of the line. In problem 6, we want the equation of the line through points -525 and 1,6, -2. Let P equal the point -525. Let Q equal the point 1,6, -2. To find the equation of a line, we need a point on the line and we need a vector that runs parallel to the line we are looking for. So what I'm going to do is form the vector PQ, which is equal to 6, 4, -7, right here. PQ, this vector, is parallel to the line we want. So again, we have the vector PQ, which is equal to 6, 4, -7, and I'm going to choose the point P, which is -525. Now, I claim I could have chosen P or Q, and it doesn't matter. I'm going to get an equivalent equation for the line. Now, we're going to express the line in 3 different ways. In the first way, we're going to express the line as a vector equation. So on the left side, we have the vector xyz. On the right side, we have the position vector of the point, which is expressed as -525, plus a scalar multiple of the vector that runs parallel to the line. So in other words, I'm going to add t times the vector 6, 4, -7. So again, this first piece is the position vector of the point. The second piece is t times the vector that runs parallel to the line we are looking for, right here. So this is called the vector form for the equation of a line. Okay, on the second form, we're going to look for parametric equations. So I'm giving you a little insight into how I think about this. I go for the vector equation first. Why? Because once I get the vector equation, finding the parametric equations become easier. Because to find the parametric equations, I just equate components. So on the left side, we have x. On the right side, I'm going to take -5, and then I'm going to add 6t. So I equated first components. Then I'm going to go y equals 2 plus 4t. And then I'm going to do z equals 5 minus 7t. So this is how we express the parametric equations for that line. Now, let's write the parametric equations over here to remind ourselves. Now, x equals -5 plus 6t. Y equals 2 plus 4t. And then we're going to get z equals 5 minus 7t. So I'll write that again here. Z equals 5 minus 7t. Now, in each of these equations, what I want you to do is solve for t. If we look at this first equation here, I claim that t is x plus 5 divided by 6. For this second equation here, t equals y minus 2 over 4. In the third equation, I can say t equals z minus 5 divided by negative 7. And so here I set myself up perfectly for these symmetric equations. And I want you to notice what I do here. I'm going to take x plus 5 over 6. I'm going to set that equal to y minus 2 over 4. And then I set that equal to z minus 5 over negative 7. So this is three different ways that we can express the equation of a line. Now, and with that, let's take a look at number 7. So suppose I want the line through uh, 0, 0, 0 and 1, 6, oh, excuse me. We want the line through 0, 0, 0 and 8, negative 1, 3. So we'll do that one. I'm going to do something very similar to number 6. I'm going to let P equal 0, 0, 0, this ordered pair. And I'm going to let Q equal the point ordered triple, 8, negative 1, 3. So PQ is equal to the vector 8, negative 1, 3. So PQ is parallel to the line we want. Okay? And I'm going to choose P equal to the point 0, 0, 0. Now, what I do, again, when I look for the equation of a line, I go for the vector equation first. So I'm going to take x, y, z, and I'm going to set that equal to the following. So I'm going to take the position vector of the point. The position vector of the point is 0, 0, 0. And then I'm going to go plus t times the vector that runs parallel to the line. So that vector is 8, negative 1, 3. So this is the vector equation. What about the parametric equations? All I have to do there is equate components. So x is 0 plus 8t. Y equals 0 minus 1t, right? And z equals 0 plus 3t. Of course, you don't have to leave it like that. We can write it as x equals 8t, y equals negative t, and z equals 3t. Now, from here, we want the symmetric equations. Now, for the symmetric equations, we get the following. Now, if we go back t equals x over 8, right? So I'm going to take x over 8 and set it equal to. Now here, t equals negative y. But if you don't mind, I'm going to write y over negative 1. And then for the last one, t equals z over 3. And that's how we do the symmetric equations. So we got the vector equation, parametric equations, symmetric equation. If we take a look at number 11, so what do we want here? We want the line through -6 to 3 and parallel to the line one half x equals 1/3 y equals z plus 1. Now, let's see if we can draw a picture of what this looks like. Okay? Now, we have a point, which we'll call P, and that's -6 to 3. Okay? And we have a line, right? And that line is represented by these symmetric equations. Okay? So we want the equation of a line through point P that runs parallel to the line L. And remember, to have an equation for a line, we need a point on the line and we need a point that runs parallel to the line. If we can find the vector that runs parallel to the line L, so if we can find that vector V that runs parallel to L, can we agree that that vector will run parallel to the line we want? Hopefully we say yes. Okay? Now this is what I'm going to do. It might be easier to view this equation as parametric equations. And we could do that fairly quickly. So what I'm going to do is I'm going to set 1/2 x equal to t. And then 1/3 y equal to t. And then z plus 1 equal to t. And so solve for x, we get x equal 2t, y equal 3t, and then z equals -1 plus t. Now, v, which is equal to the vector 2, 3, 1. So I just looked at the coefficients of t. This vector is parallel to the line. 1/2 x equals 1/3 y equals z plus 1. So therefore, v, which is equal to the vector 2, 3, 1, is parallel to the line we want. I hope that makes sense. Let's go back. So we have a line L, right? We have a given line, in other words. If we can find a vector v that's parallel to L. And remember, by design, we want the line L to be parallel to this line that we're looking for here. Okay? If V is parallel to L, V has to be parallel to the line we're looking for, because L and the line we're looking for are parallel. And we're already given the point P. So now we know V. We're all set. So let's come over here. So P is the point -6, 2, 3. And V is the vector 2, 3, 1. And we're going to express the equation of a line in 3 different ways. The first way is the vector equation. So XYZ is the position vector of the point P, which is the vector -6, 2, 3, plus T times the parallel vector. So in other words, plus T times the vector 2, 3, 1. So that's the vector equation. It's the position vector of the point plus a scalar multiple of the vector that runs parallel to the line. Okay, that's how that works. Now, if we want the parametric equations, well, I'm going to equate components. And so I'm going to get x equals -6 plus 2t. Y equals, so look for second components, 2 plus 3t. And then z equals 3 plus 1t. Now, let's remind ourselves. So x equals -6 plus 2t. Y equals 2 plus 3t. And z equals, let's remind ourselves, 3 plus t. What are the symmetric equations? So you notice I'm going from vector to parametric to symmetric. It, to me, seems like a nice logical following. So in each of these equations, I solve for t. So I get x plus 6 over 2. And by the way, I'm solving for t over here too. So I get x plus 6 over 2 equals y minus 2 over 3, which is equal to z minus 3 divided by 1. And I do that on purpose because you can peel off the direction numbers 2, 3, and 1, form that vector, and get a vector parallel to the line. So, okay, so that's how we do problem number 11. So that'll conclude this video for section 12.5, and we looked at problems 6, 7, and 11. Okay, all right, thank you.